Hi everybody, this is the second lesson in the Physics A-Level electricity topic. In this video we will look at voltage, some of the key ideas, what it is and how to work with it, and then the part 2 of voltage will be looking at exam questions and some A-star material. In this video we're going to cover the following key ideas. We're going to talk about potential difference, known as PD, and the definition of the volt. We're going to use the equation or the formula for voltage, W equals V times Q. We're going to make the distinction between EMF and PD. We're going to talk about how to connect a voltmeter in a circuit, and then the rules for voltage in series and parallel circuits. So the context example for voltage I've chosen is electric vehicles, which are fascinating technology which is going to become more and more important and used and ubiquitous as the years progress. One of the key ideas or key concerns at the moment is something called range anxiety. This is about how long does it take to charge up your EV battery, what is the maximum voltage, how much charge does it hold, and there's some really innovative ideas to address this issue. So there's an idea in Sweden where they have a lane where, using an inductive system, the battery is charged up as the car drives, and there's various other ideas as well. So this is our in context example. Before we look at the formula and the calculations, we need to have an understanding of what voltage actually is, and this is all related to energy. So we're going to imagine a very simple series circuit and just one electron, shown by the green circle, moving through the battery and then around the circuit. So first of all we're going to close the switch, and the electron moves through the battery. As it does so, it gains energy. So we could talk about an energy change from chemical energy to electrical energy, and this is shown by the electron flashing. So that's going to travel around the circuit, and it's going to be repelled from the negative terminal, attracted to the positive terminal, and it may lose a little bit of energy as it passes through the metal due to collisions, but we generally assume that that is a minimal amount. So it's only when it comes to an electrical component, in this case a light bulb, where the resistance is very high, then we're going to get a significant change in energy. So our one electron has this energy, it's still flashing, it's now going to pass through the light bulb and transfer its energy to other forms. So in this case, we're going to get light and lots of heat if this is an old-fashioned light bulb, and the electron is no longer flashing, so we assume it's lost its energy. Now, it won't have lost all of its energy, but most of the energy has been transferred, in this case, to heat and light. The electron will continue on its journey back to the positive terminal, and then the process will repeat again. So let's look at this in a mathematical way. So we've already talked about the transfer of energy. So we've got this formula here, which you should have seen before at GCSE. V is equal to W over Q. Sometimes V is equal to E over Q. So V, hopefully straightforward, that is the voltage measured in volts. Make the distinction between these two letters because they look the same but they are different. Capital V is the symbol for quantity, voltage. The capital V over here, if it's a unit, is a symbol for volts. So we could talk about the voltage being 24 volts. So the V and the V can mean different things. The work done, represented by W, measured in joules. Sometimes we use capital E to represent work done, so this is the energy or work done. We've come across charge in the previous lesson. Charge is Q, measured in coulombs. So we can see if we've got V is equal to W or E divided by Q, then our definition of voltage is the energy per unit charge. And we tend to say the energy transferred per unit charge. So we can think of this voltage as the push given to electrons to make them move around the circuit and to give them energy which they're going to transfer to other forms. So if I have 1 volt, a battery of 1 volt, what that means is I have 1 joule per coulomb. So every coulomb of charge is given 1 joule. So if I have a 6 volt battery, then every coulomb of charge will be given 6 joules. Okay, so we're going to look at some worked examples. So have a read through these questions, 1, 2, 3, 4. You can try answering them if you want to. So you might want to pause the video at this point and I'll go through the solutions after that. Right, let's look at the first one. So nice easy numbers. We have 20 joules of energy are given to 4 coulombs of charge. The question is, what is the voltage? So mathematically this should be straightforward. We've got V is equal to W or E divided by Q. As always, we write out the formula, substitute the numbers. 20 divided by 4 is 5 volts. Mathematically this is easy, but there's a really important concept here. 5 volts means 5 joules per coulomb. So every coulomb of charge is given 5 joules of energy. Question 2 is just a variation. So if we're trying to find the energy or the work done, I can rearrange this formula to make E or W the subject. E is equal to V times Q. Nice easy numbers, 5 times 12, 60 joules. We can do a similar calculation, but scale this right down to the scale of an electron. So question 3 says, how much energy is associated when 1 electron passes through an 8-volt battery? So mathematically very similar to the previous one. So the voltage is 8, but now the charge is our elementary charge, 1.6 10 to the minus 19. So we're going to get a very small amount of energy in joules. So the number of joules per coulomb in this case would be 8, but the energy for 1 electron is a tiny, tiny amount. Question 4, a little bit more tricky. This might be a difficult GCSE question or a straightforward A-level physics question. So we're told the amount of energy is 2.5 times 10 to the 5 joules. We've got the time 3 minutes, so we must convert that into seconds, 3 times 60. And we're told the voltage across the device is 12 volts. Find the current. So a good approach here would be to write out the relevant formula. So we've got joules and voltage, so it might be worthwhile writing out our new formula here. And once we find the current, then I equals Q over T from lesson 1, we can find the current from the charge. Okay, so the first part is Q equals E over V. So we've got our amount of energy here divided by the volts, so we can work out the charge in coulombs. Once we have the charge in coulombs, I equals Q over T, so our previous answer, divided by the total time in seconds, and we get our answer 116 amps. So again, some really key points here for exam technique. Write the formula, show your working, so substitute the values, write the answer with the units, and use standard form. Very, very important. Right, so we need to make a distinction between two important terms here. EMF, the electromotive force, given the symbol capital E, not to be confused with energy, and potential difference, also known as voltage, so given the symbol capital V. They are both very, very similar. They're both basically voltage, they're measured in volts. The difference is to do with the energy. Is the energy being gained by the electron, or the energy being transferred or lost by the electron? So if we refer to EMF, the definition as shown here, the energy transferred per unit charge, so that is our definition of voltage, W divided by Q, when energy is being changed into electrical energy, so where the charge is gaining energy. So this will be associated with the battery. The electron passes through, as we saw in the animation, and gains energy. So we have a transfer between chemical to electrical energy. Potential difference is basically the same. It's the energy transferred per unit charge. So it's the same thing. V is equal to W over Q. But now the energy is changing from electrical into other forms. So for example, in the bulb, we've got electrical energy, and now that is being converted into, for a light bulb, heat and light. So you could say the charge is losing energy. So very, very similar ideas, energy per unit charge, but we need to make the distinction between these two terms. Now we're going to look at voltage in circuits, in series of parallel circuits. So we can use a voltmeter, for example a multimeter, or it might be a dedicated voltmeter. The way you connect a voltmeter is in parallel. So this is very, very different to how we connect an ammeter. So generally we draw the voltmeter as shown here. So we have a circle, capital V, and what we mean by in parallel is there's a Y on either side of the component. So we connect the voltmeter across or on either side of the battery or the cell if I want to measure the voltage associated with a resistor Once again, we need 2 wires. We need to connect one on either side. What we're doing is we're measuring the difference in potential between one side and the other, hence potential difference. So in series, the voltage is shared out among the components. So what that means is if I have the total voltage of V1, that's my supply voltage, some of that will be associated with the first battery, and some of that, with the first resistor, and some of that with the second resistor. So V1 is equal to V2 plus V3. This comes out of the idea of conservation of energy, and in the next video we might prove algebraically why that is the case. In parallel, very different. We have V1 is equal to V2, which is equal to V3. So very, very different. The voltage is the same across each loop in the circuit. Now be careful, it's not necessarily true to say it's the same across every component. It is in this case because we have a very simple circuit. But if I have a slightly more complex circuit, so my bottom loop now has 2 resistors, so the total voltage across the bottom loop, V3 plus V4, is equal to V1, which is equal to V2. So you could argue that we have a series section here where the total voltage is shared between the two, and that's connected in a parallel circuit. Now it's your turn. I want you to pause the video, read through the questions, try to answer these on paper, and when you've got the answers, or you've done as much as you can, then you can play the video and see the solutions. Right, the definitions, you really need to know these. Top exam tip, write these out. You need to learn them. Voltage is the energy per unit charge, or the work done per unit charge. 1 volt is 1 joule per coulomb. And then we talked about the distinction between EMF, which is energy per unit charge when energy is converted into electrical energy, and PD is basically the same, energy per unit charge, when energy is converted from electrical into other forms of energy. Question 2, hopefully straightforward, similar to the worked examples earlier on in the video. So we're just substituting and rearranging as shown here. We need to know prefixes, so mu is micro, 10 to the minus 6, so use standard form. Top exam tip, always show you're working out. So write the formula, substitute the values, write the answer with the units, and in standard form where required. Okay, question 3. So we've got energy, 4.5 10 to the minus 3, and we've got voltage, and it doesn't say find the charge, so this is a little bit more difficult. But we know that electrons and charge are related, so I can find Q. So divide this value by 12, we get 3.75 10 to the minus 4 coulombs. And if you remember from the previous lesson, we had a way of working out the number of electrons, so it's the total charge divided by the elementary charge will give you the total number of electrons. So you should expect to get a really big number of electrons, which we do in this case. And final question, we have total amount of energy, we've got time, it says the EMF, so basically the voltage, we know EMF and voltage are basically the same. Find the charge supplied and the current, so a little bit more complex, but still we're looking at a GCSE level or a fairly easy physics A level question. So we can find Q, make Q the subject, substitute the values, and we get 1304 coulombs. And if we know the time and we know the charge, we can find I, which is the current, and you should get 10.9 amps. Okay, a quick review. Just make sure you understand these 5 questions, and you can check earlier on in the video to find the answers. There should be a link underneath the video to a Kahoot where you can practice some of the simple ideas for current and voltage. In the next video, we will look at some more difficult questions, some exam questions, and also some extension questions, grade A and grade A star.